What specific problem does your method aim to solve regarding the evaluation of large language models, LLMs?
Our method aims to address the critical oversight in the evaluation of large language models, LLMs, by focusing on cross-capabilities, which are essential for handling complex, real-world tasks that require the integration of multiple skills. Current evaluation methods predominantly assess individual capabilities in isolation, failing to capture how these capabilities interact and influence overall performance in cross-capability scenarios. By establishing a comprehensive benchmark, CrossEval, we systematically categorize and evaluate both individual and cross-capabilities, revealing the law of the weakest link effect, where overall performance is constrained by the weakest individual capability. This insight emphasizes the need for targeted optimization of weaker capabilities to enhance LLM performance in multifaceted tasks. Ultimately, our approach provides a structured framework for evaluating LLMs more effectively, guiding future development to improve their real-world applicability.
How does the proposed methodology of CROSSEVAL work? Please illustrate the process step by step, detailing how prompts are categorized and handled.
The CrossEval methodology involves a systematic process for constructing a benchmark that evaluates both individual and cross-capabilities of large language models, LLMs. First, a comprehensive prompt set is created, where annotators select prompts from a predefined taxonomy that categorizes tasks according to specific capabilities. Each prompt is then assigned a difficulty level, easy, medium, or hard, based on clear criteria that define the complexity of the task. Following this, the prompts are manually annotated to ensure high quality, resulting in a final set of 1,400 prompts, with 100 for each capability, covering all Level 1 and Level 2 categories. Finally, model responses to these prompts are collected and evaluated by expert human annotators, who rate and explain the responses, while LLM-based evaluators are also employed to assess the outputs, ensuring a robust and reliable evaluation framework.
Can you provide a simple, illustrative example of how CROSSEVAL evaluates a cross-capability task? Walk through the main steps using a specific task as an example.
CROSSEVAL evaluates cross-capability tasks by utilizing a structured framework that categorizes prompts based on individual and cross-capabilities. For instance, consider the cross-capability task of image recognition and reasoning. The evaluation process begins with selecting a prompt from the established taxonomy, such as, "Analyze this chart and explain the trends it shows." This prompt is then annotated to ensure it aligns with the specific capabilities of image recognition and reasoning. Next, model responses to this prompt are collected, and human annotators rate these responses based on predefined criteria for quality and accuracy. Finally, the performance is assessed using LLM-based evaluators, which compare the model's output against expert annotated reference examples, ensuring a comprehensive evaluation of how well the model integrates both image recognition and reasoning skills in its response.
What are the theoretical or practical benefits of using CROSSEVAL compared to existing evaluation benchmarks for LLMs?
CROSSEVAL offers significant theoretical and practical benefits over existing evaluation benchmarks for LLMs by systematically addressing the evaluation of both individual and cross-capabilities, which are often overlooked. The framework is built on a comprehensive taxonomy that categorizes tasks into 7 core individual capabilities and their corresponding cross-capabilities, allowing for a more nuanced assessment of LLM performance in real-world scenarios. Additionally, CrossEval employs a robust annotation process, resulting in a diverse set of 1,400 prompts and 8,400 human ratings, which enhances the reliability and quality of evaluations. The benchmark also incorporates LLM-based evaluators that align closely with human judgments, ensuring a strong correlation between automated assessments and expert evaluations. Ultimately, CROSSEVAL's focus on cross-capability performance highlights the critical need to identify and enhance weaker capabilities, thereby guiding future LLM development towards more effective handling of complex tasks.
How was the efficacy of your method validated? Describe the experimental design, the datasets used, and the specific metrics employed to assess performance.
The efficacy of our method was validated through a comprehensive experimental design utilizing the CROS-SEVAL benchmark, which consists of 1,400 manually annotated prompts across 7 individual and 7 cross capabilities. We selected 17 models from 5 major families: GPT, Claude, Gemini, Llama, and Reka, to ensure diverse representation, with each model evaluated on at least 5 cross-capability scenarios. The evaluation involved collecting model responses and engaging expert human annotators to rate these responses, resulting in 8,400 human ratings with detailed explanations. We employed LLM-based evaluators to assess the responses against reference examples, achieving strong agreement with human judgments, thereby establishing a reliable metric for performance assessment. The analysis revealed clear patterns, particularly the law of the weakest link, indicating that performance in cross-capability tasks is significantly influenced by the weakest individual capability, which was consistently observed across different models and evaluators.
What specific results did you achieve with Crosseval? Highlight key quantitative findings that showcase the performance differences between individual and cross capabilities.
With the CROS-SEVAL benchmark, we achieved significant insights into the performance of LLMs across individual and cross capabilities. Notably, of the 58 cross-capability scores evaluated from 17 models, 38 scores fell below the individual capability scores, indicating that models generally underperform in cross-capability tasks. Furthermore, our findings revealed that performance in cross-capability scenarios is often constrained by the weakest individual capability, consistent with the law of the weakest link. For instance, in the case studies, Claude 3 Haiku improved by 371 points in image recognition when targeted enhancements were applied, while the overall performance in cross-capability tasks increased by 458 points when the weaker capability was strengthened. These results underscore the critical need for targeted optimization of weaker capabilities to enhance overall performance in complex tasks.